It's my pleasure to start this presentation today, and it's in particular my big pleasure to welcome Klara Nahrstedt here to give a talk on navigation in 360-degree video. I give a brief introduction of Klara, which is really a pleasure to do. Klara is with the University of Illinois at Urbana-Champaign. She is a professor in the computer science department, director of the coordinated science labs. Her research interests are basically tele-immersive systems, end-to-end quality of service, resource management in large-scale distributed systems, real-time security and privacy in cyber-physical systems. But she is in particular well-known and a very eminent researcher in the multimedia systems community. She had done very influential work, was co-author of 2 important multimedia books, which are still used in my classes, although the books have appeared in early 2000s. And she has published numerous very important papers and done important work in the multimedia systems area. She has received a lot of awards. I direct you to the announcement of the presentation on the website here. In particular, I mentioned she's ACM Fellow, IEEE Fellow. She is member of the German National Academy of Sciences and received a number of other awards for her very important work. It's a great pleasure to have you here, Klara. We are looking forward to your presentation on navigation in 360-degree videos. And I give the floor virtually to you to give the presentation. Thank you very much.
Thank you so much for the invitation, kind introduction. Really, I'm so sorry not to be in Klagenfurt. My last visit, I really enjoyed the visit. Hopefully in the future, I will have opportunity again to visit Klagenfurt University and many of the researchers that I know from the multimedia systems community. So thank you so much for the introduction. And it's my great pleasure also to talk to you about some of the research that we have engaged in my research group and also in collaboration with researchers from University of Massachusetts, Amherst, Professor Mike Sink and Professor Ramesh Sitaraman and his students. So I do want to tell you about this particular project and some of the insights that we got over the last couple of years as we started to look at the 360-degree video as one of the dimensions of the visual media that is currently coming forward. And I want to talk about the challenges, some of the solutions that our National Science Foundation funded project between UMass and Illinois is starting to see, and also some new opportunities that we see that could be happening within this particular space. So I do want to first motivate the 360 video delivery systems as a new or sort of the continuous addition to the 2D video delivery and the challenges. And then we will talk about navigation graphs as a potential concept, as well as various data structures that we think might be important to start to bring into the overall DASH framework, which is very well known from Klagenfurt, and this particular research group of the researchers in Klagenfurt have been very influential in the DASH space. So we would like to sort of bring to the community sort of new spaces to think about. And then, of course, there are some opportunities in conclusion. So I think we are seeing major results of the 360 video where people are starting to use the Oculus or other type of virtual reality head-mounted displays and then watch different types of content. And what currently this kind of head-mounted displays and then the content, the 360 content allows is that you might have multiple viewers that can actually view the same content, but very different views. They can follow a woman, for example, as on the picture shows, can follow the player number 10, and the male viewer basically can watch the player number 4. So these applications are coming. And the reason actually is that new devices are coming. I find that multimedia systems community always is very active when new hardware comes out, and then really thinks very carefully about what this particular hardware can do for the multimedia systems community in terms of new content, new systems, new protocols, new resource management. And the 360 cameras actually sort of came out. And the reason is that the lenses, the 2D lenses, started to become smaller and smaller in their form factors. So you currently have these cameras that there are multiple 2D lenses basically collocated in one bulb. And so you can then post them on a stick and then basically capture the 2D views sort of together. And so we have currently, particularly in our group, for example, we play with the GoPro type of cameras. We have actually also experimented putting together our own 360 cameras. And these 360 cameras then are then creating sort of really cool images, right? And cool videos of very sort of distorted or very different types of views. And so the artists and entertainment has been using the 360 camera imaging, these panoramic sort of views in various movies and for special effects. But sort of more seriously, you know, the 360 video is a you know, medium which captures multiple 2D videos together with their metadata, and in some way they then need to be stitched together to actually create this kind of spherical video. And then this particular spherical video would be best to encode and store somehow on the storage or basically deal with it so that it can be transmitted and then basically displayed. So in order to do that, in order to sort of then really process it in this digital space and virtual space, one needs to look at this spherical video. There are not very good formats for really capturing sort of the whole spherical video. So what the researchers are doing at this point, and these cameras are providing as an SDK, as an interface, is projections actually of this spherical video to a 2D representation. And then this particular 2D representation that we will talk about is then being used for processing, for storage, for partitioning into the packets, to basically distributing. But then again, in the display, one has to sort of recreate the spherical video so that you can show the different views. So let's sort of talk about some of the concepts that currently the 360 video community is working with. One is the field of view or viewport, where we currently basically take a slice out of the sphere, and it's a fraction of the view of the scene of the 360 panorama. The angle currently, what would be sort of optimal, is usually 120 degrees. And that sort of delimitates what is the sort of viewport and viewport center. The other really important issues with respect to the 360 video is the resolutions and the frame rate. As I started to talk about, the 360 video is anticipated that the future viewing of 360 video is going to be via the head-mounted displays. And that means that the display will be very close to your eyes. And that actually also means that you will have a very clear understanding of when there are a lot of pixels or there are basically distances between pixels. So in order to have a really good experience with respect to viewing this 360 video in your head-mounted displays, we will need to provide high resolutions that we are not used to actually on either on our laptops or on even sort of our phones and so on, but it's getting there. So 4K, sort of 3840 by 2160 pixels will be required to have a strong, and even higher, so 8K, 12K, people are talking about that kind of resolution of the same, of one frame, basically. The other important issue is, again, as you are bringing these devices closer to your viewing devices, to your eyes, we need high frame rate. Definitely the refresh rate, 100 hertz, 100 frames per second. As you know, already in the television, to have a avoidance motion, flicker issues, and so on, to basically have 30, 60 frames per second. But in these head-mounted displays, even higher frame rates are expected. Another really important issue is the motion to photon latency. People are now very much talking with the VR, AR, as well as with the Video 360. And that has to do with the head-mounted displays, that basically the head, as you are moving, will be driving actually what content you want to see, right? If I am looking straight, I want to see the view of the straight. When I am looking basically to the left or to the right, I want to see from the sphere basically that particular view. But what is happening is that basically you might not have all of the pixels now available in the in your head-mounted display, and we will talk about it. The bandwidth for these delivery systems is enormous, right? You think about 4K times 100 frames per second. So you are talking about tremendous amount of data, much higher than currently television or sort of your laptops might be delivering, or your Zoom video delivers. And so therefore, we will have to think about, as multimedia systems designers, how do we partition this particular 360 video? But that actually then puts a tension on this motion to photon, that if I move my head to the left or to the right, I want to see the content, and how do I make available that content below 20 milliseconds, right? That's currently the VR expectations. And of course, the resolution time, the frame rate, gets translated into the bit rate. And so we are at this point expecting, well, if it's 8K, 60 frames per second, 100 megabits per second. You know, then we need to look at some codings and decoders, what to do. So one other thing that this particular 360 video is now very much assuming and anticipating is that the spherical video will be divided into independent tiles. So if I currently go back here, right, as you are currently sort of looking at the longitude and latitude, right, you can actually divide these this sphere into these various tiles, right? And then you are sort of stitching sort of the tiles. So that's currently really the spatial divide of spherical into the independent tiles is assumed. So I also mentioned that these particular tiles and the spherical representation is great. And I think this is currently the big sort of challenge for the computer vision and for the multimedia systems community. How do we sort of represent this particular sphere in a much more realistic way? The current representation of this sphere is a projection into the 2D space. And so this sphere to plane mapping, right, is currently the way that many of the industries and academia are going. But the moment you start to do projection from the sphere to the 2D representation, so that you can store the data as files, you can transmit it as packets and cache it and manipulate it, you are seeing certain problems, and that is the viewport distortion and the spatial quality variance, right? That, for example, we will be talking about most of the representations and sphere to plane mappings are in so-called equirectangular representation. And that actually means that the least distortion will happen around the equator. But the more you go to the poles, the more sort of the stretching and distortion of the viewport happens, as well as spatial sort of distortion is there. So this particular consideration needs to be taken into account. Therefore, also the viewing probability, you know, which particular tiles you are going to be needing to see in full quality or less quality, I think becomes really important. here are some of those projections that I mentioned. This is currently over the last 5-6 years. Many companies actually, Oculus and now basically Facebook are looking, for example, at the cube map. But as I mentioned, most of those, for example, the GoPro, and we are currently also working with Ricoh cameras. These cameras, 360 cameras, are providing us with this equirectangular projection, and then stretches the poles, reduces efficiency of coding, and so on. So a lot of research, as you can see, based on the publications, basically this research has been really now for the last, I would say 3, 4, 5 years, trying to understand these particular projections. The second really big issue is that is currently being pushed more and more into the hardware, but there are also some software solutions in stitching. I mentioned that these 360 cameras are 2D lenses, and so you need to do sort of stitching. But in the stitching, there is also sort of various issues that people need to consider, and that is, for example, a careful calibration and feature mapping, because basically you could have this particular sort of tower that if you are, this is currently one 2D video frame, and this is another 2D video frame. If you don't stitch them, probably you have a sort of shifted type of sort of tower, right? So vulnerability towards problems in stitching, and pay attention to that as you are currently buying or working with the 360 videos. There is also a vulnerability to excessive delays, and as you are currently stitching sort of various frames, that it takes time, and so the cameras are in camera production industries are currently trying to do it in hardware, but currently mostly you have two lenses, or you have 4 lenses, so the coarseness is still there. So that's actually why people are currently building sort of multiple lenses, eyes, and then try to sort of stitch them in software. But that actually takes time, right? So the stitching. So I do want to talk about streaming. So one thing is what happens on the camera side, but then actually what's happened on the streaming side. And currently, the streaming is mostly done through the YouTube, where you basically do capture mostly in non-real time the content, you stitch it together and you put it out onto the YouTube servers. So real-time streaming is coming, the hardware is coming, but still, processing and is still sort of slowing down in order to do sort of a 360 teleconference. But as I said, it's coming. The hardware is getting better. But for the on-demand, people are looking very much into the Dash framework. And in the Dash framework, as you know, it's basically dividing the video into segments, and every segment then being encoded at different bit rates. And this particular mapping and information about the segment to bit rate information is stored in the media presentation descriptors. Basically, as the clients, the viewing clients, Dash clients are viewing the video, they also have the capability of adaptive logic and control logic to actually determine, based on their bitrate that they are observing on their device, to actually request the corresponding segments of their video. These particular adaptation heuristics will be even more important to the 360 video if we are sort of really aiming, and I think we should plan sort of to use the Dash framework. So what then does need to happen is that you do have the content creation, stitching to the spherical video, and the projection has to happen into one of the plane representations, for example, equirectangular video. But then basically that particular video needs to be prepared into sort of tiling, encoding, but into these multiple representations for the multiple tiles. And then now basically it becomes also really interesting is not only that the segments have different bitrate, but now basically every segment is not just the number of panoramic frames for a particular time interval, but now also every frame divided into tiles might have different bit rates. So it definitely increases the complexity, but because you don't need basically all of the content, you might basically the viewport user might request certain viewport. That particular viewport then needs to be translated into the tiles, and the tiles basically need to be translated based on the bandwidth that you are currently seeing into the bit rates, and then basically you are requesting chunks of the video of that particular bit rate. And we will talk about particularly what we have done in this particular space, how to organize the data, how to request and predict sort of some of those issues. So those are some of the challenges that we need to think about it in comparison to the 2D video, which had a much smaller resolution, much smaller frame rate. Now, basically, with the high video rate, high resolution, we really cannot think about sending everything. Now, YouTube currently has very short clips of 360 videos, and they download everything. So it's really basically almost like a FTP. You are downloading the whole frame or big chunk. They are not doing tiling, but you basically download everything, and then you allow people sort of to roam around that particular video. But if we are thinking about longer videos, longer movies in this particular format, one knows that 80% of the bandwidth is really not used when you are watching it with the head-mounted displays. And so removing the non-visible parts that makes very much sense in the 360 video. And the current status is that you really try to identify which particular tiles belong to the viewport that the viewer is currently looking at. And so you try to identify this particular viewport and represent it. This particular viewport represented only spatially is basically captured in another data structure that then the server, the Dash server would keep, and that's the spatial relationship descriptor. So that's the SRD is sort of really useful to keep this particular information. But selection of viewport tiles in space and time needs to be, again, part of the overall Dash framework. And then these adaptive and predictive choices of representation of future viewport tiles need to be also part of that Dash client adaptive logic, as well as the representation sort of on the server side. And the last thing that I want to talk about as challenges is really navigation within this particular video. And this was something that I think we feel that some of the work that we have done and insights that might be useful to the overall Dash framework. So the navigation is really important with 360. If you are thinking about, you have all of the content, what's happening around you. If you have head-mounted displays, you are basically having your head that navigates where you are currently looking at, and that you have to really watch them for the motion delays, and they're corresponding to the motion to photon delay, less than 20 milliseconds. If I have 360 video on your mobile phone, right, then usually as you are tilting up and down the particular mobile phone, that's your navigator, right? And you need to respond to that. So if you navigate too fast and you don't have all of the viewport tiles, you start to see basically blank spaces, or white spaces or black spaces, basically, but you are diminishing the quality of experience. And usually the YouTube videos will provide sort of a little navigation button that you can navigate. So navigation is important in these 360 videos as we are watching content. But I do want to show you through this particular video. This is a blue whale by Weird company. This is currently the sort of little navigation part, but I actually want to navigate. You can navigate it this way. And the nice thing is it allows you, right? So this is currently the regular dash that it downloads the whole sort of set of frame as a segment. You can navigate. You have all of the views and viewports available, right? There is no, suggestion basically what you should be watching, and you can actually end up viewing, maybe something here. What's the old ship, and so on. And this particular viewing allows you to do that. But what does happen is that maybe you miss a really, really important aspect of the video, what the creator of the video wanted you to see, and that's basically the big whale. You might have some context, which is the audio, right? But otherwise, if I would not have known this is a blue whale, I could have actually stayed, for example, in this view and totally miss the big blue whale, right? So we felt that as we started the project that also as we allow the content, the 360 content, to bring in some better navigation and hints. And this is currently actually the goal of that project that we are working with Mike and with Ramesh to really get understanding of how do we create cues, how do we create events to alert a viewer who is browsing, for example, in the 360 space. So, the challenge also is, as you are currently navigating, and if you are only downloading 20% of the tiles, how do you predict what's the next? Where does the user going to be navigating, with his finger or with her head, right? So, and this particular picture sort of shows that I have currently a playout here. This is currently my buffer queue, right, on my Dash client. And this is my Dash server. And there is a latency, right, between the server and the client. Maybe you have a proxy like Akamai, and they basically want to maybe cache something, but you still need to somehow predict, needs to request for future segments based on the predicted viewport. And if you predict it, for example, based on whatever you are currently watching, you might actually maybe request this particular set of tiles at time t0. So you get sort of the new frame or new segment, but the viewer basically in time t1 moved to another set of tiles, and you don't have it in your buffer, right? So, so that's currently where some of these issues are, around 360, and I think we are still not quite there, particularly in these photon motion to photon latency predictions. Accuracy. So I do want to start talking about a solution as a navigation graph to start the discussion with this particular research community, but also others. How do we capture what is happening in these 360 content that can help them in the streaming, in the prediction, and in the viewing? So the concept that we are currently exploring is a graph representation, and that would be attached to a stored video 360 on a Dash server. And so in this particular case, we are still looking at segments of a size 1 to 15 seconds duration video chunk. But now basically we are looking at 360 video divided into tiles. In this particular video, we are going to be dividing into visible tiles and non-visible tiles. And we want to basically download on only the visible tiles. And so there is a viewport, right? And this particular view or viewport basically over a particular period of time, right, of the segment. Here are currently the viewport visible tiles, right? And this is currently on the y-axis, we have the tiles 1, 2, 3, 4, and on the x-axis, we have a time going, right? The segment L0, L1, L2, L3, and so on of the particular time. And so over this particular time segment, we will be seeing in this particular viewport tiles 1, 2, 3, 1, 2, 3, then this is 2, 3, 2, 3, right? So over all the visible tiles in this segment, there'll be 1, 2, 3. And the same, the next segment will, as the viewport moves by the user, will be 2, 3, 2, 3, 4, 2, 3, 4, 3, 4, right? So then the union of all these visible tiles over that particular segment is 2, 3, 4. So these are some of the basic concepts that we want to then bring into a navigation graphs. And we are going to consider two different navigation graphs. One navigation graph is a navigation graph at the user side. And at the user side, the particular client can only monitor basically his or her own visible tiles that he or she has been seeing, right? So currently on the client side, we are going to be capturing, I am currently seeing visible tiles 1, 2, 3, that's the state S0. Then I would go to the state S1, seeing tiles 2, 3, 4. Then I go to sort of state S2, sort of seeing, 3, 4. Then going back to the 2, 3, 4 tiles, and then going back to 1, 2, 3. So this particular graph represents basically what does the user currently, as he or she is watching the video, which particular state of visible tiles he or she is. This particular graph then gets transmitted to the server, and the server collects actually all of these different viewing patterns of the clients and creates actually based on multiple clients the so-called viewing graph. And so this particular graph V0 has the segment, right? And it basically then looks at, for the same video, multiple people have been seeing it, multiple people are submitting these viewing graphs, their own viewing graphs, and it basically then sort of per segment, it looks at what was the set of visible tiles that have been sort of seeing for this particular movie in this particular time, 1 to sort of segment 1, segment 2, segment 3. So video server collects viewing data from the clients and creates this kind of viewing graph over the movie duration based on multiple viewers providing feedback. And then, of course, every client has its own views. And then basically the video server has a video segment, has the media presentation descriptor, and has a part of the sort of navigation graph. So let's now explore this particular navigation graph. How are we currently sort of using it for view capturing and prediction? So the applications of the navigation graph, you can use even the server. We currently explore and offer that the server can keep multiple users navigation graph and provide then prediction which particular next tiles per viewport needs to be transmitted. But you can also use just a single user view transition, right? You have the view transition matrix, how you go from one view to another based on your own experience, and you can basically use that for prediction. Usually the predictions are a little bit weaker, or based on single user. Based on the cross user, we will see basically the view transition is much better. Many people are sort of strengthening, certain views are interesting, and therefore people are watching it, and so you can get better view transition probabilities and better prediction which particular tiles need to be again sent to the new viewer that is coming to view the same content. The next thing is not just to look at viewport to the tiles, but also keep track, and we will talk about it, object level view navigation. And I will talk about that. And the last thing that we are currently working on, I don't have solutions yet, but it's the storytelling. Remember, I mentioned with the whale that in some way, at the end, what I would like to see is that we make a much better assistance to the directors, to the creators of this 360 content. We can provide hints from the creator, from the director of this 360 video to the viewers, what they might want to see. So let's go to the view-based navigation first. So on the server side, we are getting the various clients' viewing behaviors. And so we can actually start to create on the server side this viewing graph. Basically, this is currently, we have 3 clients, right? And the first segment in the past, L-2, would be watching Viewport with tiles 2, 4, 5, and 7, right? This is currently that particular viewport. And let's assume that in this particular segment, all the clients start, right? The movie starts. But then actually the clients go in different ways. And so we currently calculate a conditional probability based on the number of viewers visiting the previous view and how many number of clients are moving to the new view, right, to the current view. So in this particular case, we have 2 different views. One view is the one that we are staying in the same view. And this is currently 2, 4, 5, 7. But then there are 2 clients that are going to a new view, and that is visible tiles are 5, 6, 7, and 8. So we have 3 clients that have been in the previous view, view 1, and then moving to the view 2, which is basically the same view, is 1/3, and in going to the new view 5, 6, 7, 8, in the next segment, we have observed our 2 viewers. So we are currently, and then you can continue. This is currently, for example, this particular viewer goes to a new view 5, 6, 7, 8. All right, so we are currently going to the 5. And again, in this particular view, there was only 1 viewer that went from the view 2 to view 5, right? So it's 1/1. But now basically going from this particular view to back to the 2, 4, 5, 7, there are basically, there were 2 viewers in the V3, and then 1 viewer moved to 2, 4, 5, 7, and so on. So I think you are getting sort of the gist of that, creating this particular navigation graph. All of these navigation graphs are basically being sent to the server. And so you can, based on the past behavior, create actually what happens and create this particular sort of graph of viewing behaviors. On the client side, the user, as the user is currently viewing things from the past, it can basically calculate the same. It has the state of the visible tiles. For example, in this particular case, 4, 7, 10, and 13. Then it basically moves to the viewport of 7, 8, 12, 13, and 14. Then it stays in this view and then goes back to 4, 7, 10, 13. And again, you can create conditional probabilities of number of times visiting the tiles or visible tiles from the previous sort of segment and the number of transition from the previous segment to the current segment. So here currently, because I'm just a single user, I have visited from one previous one to one current one, so the probability is 1. But basically here currently, as I go from this particular port to this one, I actually have visited 2 of these ports, and then am I going to, for example, and I'm going to the S1. So this is currently 1/2. So you are currently then looking sort of the accumulative viewing behavior of your own behavior as you have been watching the video. So you are creating these particular graphs based on your sort of behavior or the server behavior based on the clients. And then basically you could use this particular past behavior to predict, right? What would be the probability that you go from this particular state 4, 7, 10, 13, going to your new state, maybe to other sort of 7, 8, 13, and 14, right? And you look at the past behavior, what happened if the user was in a conditional state S1 and then moved to S2. And this particular example, we had 1. So you assume that the user will sort of stay in the same viewport. But of course, as far as you go farther into the future, right, it's becoming sort of matrix multiplication, because you have to look at the many, many probabilities. I am currently not only going from S1 to S2, but if I'm in S2 and I'm going to the segment L+2, I might actually consider what happens if I am in the conditional previous state S2 and I might go to S1 or S2, right? So, or even new state, right? So the probability basically become smaller and smaller. And the same thing actually happens in the cross-view navigation predictions, right? That if I currently want to predict where would I be from segment L to segment L+1, you basically are currently in the viewport V1 conditionally, and then you might need to consider what happens if I go to the viewport 2 or viewport 3, right? And it becomes again, sort of matrices that you need to consider, and you might sort of weight, give sort of higher weight to one view versus the other one. And of course, as you go further and further, that particular combinations basically become more and more, and therefore probability becomes. This is currently one of the sort of challenges if one sort of, you have to take some kind of prior behavior, but you are hoping that, particularly with respect to the cross-user, that the probability, for example, this is currently 2/3, you assume that more viewers actually will go from view 1 to view 3, because in the past you have seen this, and so you can then predict that that's probably what you will expect from the new viewer. So that actually then, if you have this kind of view predictions, either just using your own past behavior, then you might use it actually for the rate selection. On the Dash client, as I mentioned, there is the adaptive logic, and the adaptive logic actually does decide what is the bit rate for the next segment. In this particular 360 Dash approach, we need to consider not only the throughput estimation and the buffers and the buffer status, for example, like BOLA or some of these other caching algorithms, but for rate selection, but also the certain prediction, what will the viewer want to see, particularly because now we are not talking about just getting the whole frame, we are talking about just visible tiles that we want to download. And so taking into account the single user prediction or the cross user prediction for the rate selection is very important, because then you actually decide these are the tiles and with this particular bit rate to take in. So we have implemented this particular original sort of very first system where we had sort of Oculus 360 video framing, and what we have done is we had visible tiles, and the visible tiles are really the green ones. But we also felt that when users are looking at, there's a very sort of clear viewport of maybe 100, 120 degrees, but we actually also took the tiles around that particular high quality visible tiles and considered those also as visible views tiles. And so we had a medium, and then actually whatever we didn't have we did also transmit, but with a low quality. And so you can see currently that where the action happens, right, there is the green tiles. Those are the highest quality, highest bit rate. Then some of the neighboring tiles around that particular action, we put medium quality, and then whatever bandwidth still was remaining, we put sort of low quality bitrate. But you could think about that. If you don't have enough bandwidth, you can just drop the low bandwidth, and then it becomes sort of blank frames. So I do want to talk about the continuation of the work that we have done with respect to objects. So one thing that we felt that the viewport to tiles is important, but also one needs to start to consider the persons, and we saw actually that people are following certain actions and certain objects as they are currently viewing. And even more, actually, we then analyzed various videos, quiet videos like the Conant, or very high performance skiing, where we can actually see currently object appearance, right? And the object appearance in terms of tiles. So this is the segment, and on the y-axis you have the tiles, and you can see the Conant actually, because his head is sort of in the that you watch that particular state in quite steady tiles. But if you currently look at, for example, the video 8, right, which was the football, right, the tiles constantly change because the ball currently, the players are sort of moving. And so one does need to consider that the viewing patterns will be very much changing. And so one thing is that one needs to consider not just the viewport to the tiles, but also the semantics. And so that actually led us to developing another data structure. So we have now in the Dash server not only the media presentation descriptors, the spatial relation descriptors, but now the navigation graph, the viewport to the visible tiles. But now basically we introduce semantic flow descriptor and the view object navigation graph. We currently call it sort of VONG. We sort of renamed it a little bit because I think that sort of reflects more what we are actually doing. And so what we are actually currently proposing to the community is that we bring in more of these. This is all offline. You can calculate these particular information offline, but they are then really helpful as you are starting basically to stream data to the Dash client. So let's talk about a little bit about these new sort of data structures that are helping in the streaming. So one is the semantic flow descriptor that basically does data analysis. So we do machine learning, object detection of the particular movie, and then actually map it down to the tiles. So this is not, viewport is basically a whole sort of sequence of if the object is there or not, but this is currently where you are looking at. But the object sort of specification is really where the object is, all of the tiles that are currently embedding the particular object. So this is currently, for example, 4 and 10. The car is currently, when we detect the car, we then map it down to which particular tile it entails. This is tile 15. And of course, then we are analyzing it as the segments go from the previous segment to the next segment. And this is currently the car, the user moved to 5-7 tile, car moved to tile 13, and so on. And then the user, for example, another user maybe moved, another user showed up, and there is basically another object in the tile 11. So analysis of that particular movie with respect to these SFDs is really important. Another analysis that we do on the server side, offline, is really having a viewport to the object. And the reason is that basically we know people are looking at particular sort of space, and it's a whole view, right? So the view to the object calculation is really important. And then actually also the probabilities that you go from one viewport to another, and that basically sort of is correlated to which objects you are currently looking at. So we wanted to create a navigation graph with respect to the state of moving from one object to another. And the probability of this particular objects that currently number of clients visiting certain state or certain object, right? In the previous segment, this is on the denominator, and then basically here it's number of clients change their states from previous object to the current state. So here, for example, you could think about it. We are currently having 4 and 10, and this particular viewer, sort of moved with the object and going to the next sort of 5 and 7, right? And then there's the viewer 1. So really correlating the views and the objects basically as you are currently moving from one state to another. Again, based on multiple users' feedback that is coming to the server. On the client side, the important issue is basically the view prediction, right? The viewer, remember, has to decide basically which tiles do I want to actually watch for my next segment, right? And in what bitrate. So we currently, which object sort of the viewer will watch, we want to sort of determine, this is currently based on the head position, what is currently the viewport, and the viewport basically maps to the objects, right? Or you are sort of following which particular objects. And then basically we also are downloading to the client not only the view object navigation graph, but also to assist the adaptive logic on the dash. We also download the SFD, the semantic flow descriptions, right? So this is the object to the tiles. And now basically on the particular object, based on your head movement, you can start to create so-called view motion vector. And also based on the SFDs, you can calculate basically where the other users have been moving in terms of motion. So we do calculate the view motion vector, and that basically gives us a prediction that this is currently where the viewer will be probably following which particular view, which particular object, and therefore which particular tiles. So I want to just very briefly show you some experiments that we have conducted. So first of all, we needed the head mounts, head-mounted traces. How do people move for particular videos? So we picked from the MMSys 2017, there was a really nice data set from 9 videos. These are currently the videos that we have been exploring in terms of their dynamism of the objects and their tile positions. We also looked at tiles with different representations, and we used for the object detection. Remember I mentioned that on the server side, you do offline object detection. We use the YOLO version 3 for the object detections and tracking to sort of create some of the offline, these kind of semantic flow descriptors and also the view to object graphs. And then actually we wanted to also compare the navigation graph if I don't have an object consideration and tracking versus just views to the tiles. Now basically I have a view object and tiles. We also wanted to look at just a simple linear regression and then the ideal sort of view and then also mono. In terms of conditions, we wanted to look at if I have a wired sort of constant throughput versus variable throughput capabilities, because that drives then basically also what kind of tiles you need to get and your adaptive logic on the dash client. So here is currently some of the streaming performance. As you can see here currently, the CWare, which is taking into account view, objects, and tiles, versus the navigation graph, which takes only the views and tiles, versus basically the ideal. So the ideal, of course, has the video PSNR, peak signal noise ratio, the best, but the CWare is coming quite close, right? So this means actually that if you think about what you need to deliver having understanding of semantics, what the viewers are watching, I think can really help in the client decision-making, which particular tiles to request and then what bitrate. Also, another thing that I wanted to point out is metric is really how many average blank areas you have, right? And that means that you missed actually to bring certain tiles that the viewer wanted to see. And you can see actually, of course, the ideal has almost 0, right? Because you have an ideal prediction. But the CWare does quite well, particularly when you have more quiet videos like the Conan, right? This was the video 1. The skiing, we have done sort of okay. The football, right? We have done, this is 8, and so on. On the mobile network, of course, the signal noise ratio is a little bit lower. There is much more adaptive bandwidth, and then, but again, the CWare did perform well with respect to these various different categories of the video. And again, blank area was the mono, when you have basically no statistical differentiation of the tiles, really doesn't perform well. You have a lot of blank areas. We did look at storage, right? You can sort of think about it that this is currently quite a bit of data, metadata that you have to carry on these servers. And so per video, the semantic flow descriptors, right, from the objects to the tiles, the information around 100 kilobytes, the view to object navigation, 10 kilobytes. And so the processing time, right, you have to create these particular sort of metadata is 4 minutes because you need to do object detections, and then the view to object, once you detect the objects, the view mappings are faster. But then the online actually view prediction is very, very fast. So, and that basically then reflects itself also in terms of the precision. The CWare actually had a much higher precisions across the videos that we had from the MMSIS 2017 data set. Prediction errors are really important. Again, this has something to do with the sort of with the blank areas. But here currently, particularly some of the predictions where so Navigation Graph, for example, did quite well, sort of particularly in the near future. And sometimes with these particular objects, it's the precision is higher, but also prediction errors could be quite high, particularly for the CWare. And so because you have so many views potentially to sort of consider an objects, but in terms of some of the, if you start to consider sort of the visible tiles plus the surrounding tiles, the CWare getting sort of those tiles is very good. So opportunities for other research was definitely multimodal content. We have currently looked at the video only, but ambisonic video, audio, accelerators, touch, smell should be considered in this particular space. Particularly, I think, as the object prediction can help, and where are currently people looking at can be beneficial. Particularly in your accuracy and sort of performance. I think that sound or some of the more accelerators, basically, if there is some sort of vibration, can sort of help what's sort of happening in the content, could actually help us in the event detection. Also, I think we need to work even more now on low latency protocols to enable the AR applications, volume, and how do we combine 360 videos with volumetric videos, with virtual graphic object, right? The whole visual space is getting very rich, and connecting it, synchronizing it with multiple directions of sound and other sensors, particularly if we want to actually deliver this particular multi-modal content on resource-constrained mobile devices. And the really question is, how do we use machine learning and AI in caching and transmission? Can we learn actually from what is happening with respect to content, with respect to the viewing, and that helps basically in the decision which particular tiles to cache. And on the quality of experience, we just started, but there is quite a bit of VR work on cyber sickness. But now in the Video 360, sort of explorations need to happen. We need to look at much more careful at some of the missing objects and content, right? I mean, some of the precision errors. What kind of impact does it have on the cognitive capabilities, right? We don't quite understand that. What happens if the user gets lost in this particular content? So ability to follow storyline, and this is currently what I mentioned. How do we bring hints from the directors, from the creators of the content? And then standards for executions of these VR, AR subjective assessments. I think we need to get aid from sensors in head-mounted displays to determine cyber sickness, other QoE issues, I think need to be explored. So in conclusion, so I was presenting sort of some of the research that currently I am engaged in on Video 360 delivery, navigation. Progress has been made in acquisition, streaming, and displays, but I think still more work needs to be done. One of the solutions that we are bringing to the multimedia system community is really to consider this navigation graph, how to represent how people are moving and viewing the content, how well does it sort of maybe can help in prediction of the, for example, access points to decide which particular content to bring in, really sort of we started basically to look at some of the view predictions. But as I mentioned, you have seen some of the probabilities, statistically, how well we can do when we have views, when we have objects. But I believe that in these view predictors, we still need other contextual information. But we saw actually that the object view navigation graph can actually help us in prediction of the performance, PSNR improvement, accuracy improvement. And we believe actually that this particular navigation graph can be also help in volumetric media with 3D tiles, and that's going to be next consideration. And I just want to acknowledge my collaborators at UMass and also the National Science Foundation that is funding this particular research. Thank you.
Klara, thank you so much for this excellent presentation. So many aspects were covered of 360-degree content, from capturing to navigation and consumption. Thank you so much for